Yes. From yesterday's class, I told you about spring pendulum. You have a rigid surface about which you have a spring. I told you this. This is in gymnastics, we can see, in gym, we can see. This is a spring and there is a handle. So when you extend the spring, you cannot extend it beyond a certain range. That range is called Hooke's law. That's what you yesterday asked me that question. Last question you asked me a doubt. How much we can extend? We cannot extend a lot. If you extend a lot, the spring will break. And you cannot compress also a lot. If you compress a lot, then also the spring will become, finally it will become a small one. It will not further again extend back to the original. It won't restore backwards. So see, if you compress the spring too much, it will stay back like this. It won't come back. So you have a limit of extension and limit of compression. That is called Hooke's law. That is the next chapter anyways. In elasticity, we will learn. Then I told you F is equal to Kx. I told you. Yesterday I told you F is equal to Kx. And I also told you what is K. And the same F is equal to Newton's law, mass into acceleration. Yes or no? I told you this. And this K is minus K. F is equal to minus K. Why minus K?
Yes, sir.
That also I told you. When you are pulling the force, pulling the spring with a force F this side, it will restore in reverse direction. That is why F and X are opposite to each other. Yes. Then I also told you what is the acceleration in S.H.M is equal to minus omega square x. And then we compared both of this. Yes. Minus cancel, x cancel. Then we got that. Understood? You remember? M omega square x.
Yes, sir.
Yeah, here M is there, A is there. So F is equal to MA. So MA is equal to Kx. If you substitute, you just equate it. Minus cancel, x cancel. What further finally you got is omega square is equal to K by M. Omega came out to be root K by M. And we also found out time period is given as 2 pi by omega, which is equal to 2 pi M by K. Yes, I told you all this yesterday. Now, having known this, next important thing is energy consideration. Very important. This is a 4-mark IP answer. Sometimes earlier they used to ask as a 8-mark answer. Now they are asking as a 4-mark answer. So this is energy considerations.
Yes, sir.
Or energy in S.H.M, simple harmonic motion. Very, very important answer. Even in your NEET also. Energy in S.H.M, simple harmonic motion. What all energies that a simple harmonic motion oscillator have? So let us understand that. There is a body here. When I say S.H.M, two things should come into your brain. First thing is what? A spring. A spring is oscillating. Second thing that should come into your brain is simple pendulum. Either of them, both are oscillating in x-axis only. Both of them are oscillating along the x-axis only. So the spring, what I told you, spring. Let us take a spring only, easiest case. Spring attached to a ball or a bob, and it is oscillating like this side, along x-axis. So when it is oscillating, there it is moving, no? When it is moving, any body that is moving is assigned with what energy? Velocity is there means kinetic energy is definitely there. Kinetic energy. Yes. Kinetic energy is there. Because it's moving, therefore kinetic energy is there. What is kinetic energy? K. Half M V square. So half M. What is V? Go back to yesterday's class, you will know what is velocity of S.H.M. I will write it again. Just go back to yesterday's class. What is velocity? I will derive it again for you. Yesterday, what we wrote as x is equal to A cos omega t plus or minus phi. And then we wrote velocity V is equal to A. Differentiation of these, remember, velocity is defined as d by dt of x.
D by dt, sir.
D by dt is differentiation. Cos becomes sine, I told you, remember?
Yes, sir.
And Cos becomes sin, along with that something else also happens. What happens? This omega will come out. Yes or no? And cos becomes
Yes, sir.
sin with a negative. So minus a
Yes.
omega sin omega t plus or minus 5. Remember this yesterday I wrote? So we got velocity equation. We have to substitute it here. What do you get then? Half. Instead of v, we have to write this. Omega sin omega t plus 5. See, check the brackets carefully, children. See here, this bracket and this bracket. So to avoid confusion, what I will do is I'll put a squared bracket here so that there will be no confusion. And I'll put it in some other color also. See this? Now you understood? A square. Because this is velocity, square of the velocity. Understood this? What do you get? Half. E square means what? E square, omega square, sine square, plus or minus 5. Understood what I wrote? Understood? Now
Yes,
we
sir.
know very well from the earlier knowledge of spring balance, we know what is K. What is K? K is m omega square, isn't it? See this K is written here.
Yes, sir.
K is nothing but m omega square. So can I write this m omega square? I can rearrange this as half. A square, put it aside. M omega square, I'm putting it nearby. Sine square, I'm putting the terms in rearranging order. Of course, there's a plus or minus. So m omega square, can I write it as k? Yes, because you see, it's there in the earlier case. So now we can write this as half. I would write k a square or a square k, it is the same thing. So k a square sine square plus or minus 5. Understood this? Understood what I wrote? Is it clear?
Yes, sir. Clear.
The same thing I can write it as half. I can put aside and write k a square sine square omega t plus or minus 5. Now this sine square plus or minus 5. This is very important for us to understand. What is sine square? This is not there in your textbook, but I am telling you. What is sine square theta and cos square theta? How are they related? Do you have any idea? 10th standard we learned. Sine square theta plus cos square theta equal to 1. You know this trigonometric identity?
Yes, sir.
10th standard. So from that, we can say that this whatever there here, sine square of something is there. Sine square of theta can be written as 1 minus cos square of that. Yes or no? Yeah, can write it like that. 1 minus cos square theta we can write. So can we write this as half
Yes, sir.
k a square 1 minus cos square of that whole thing omega t plus or minus 5. Okay. If I open these brackets, I would get half k a square first term minus half square cos square t plus or minus 5. This is what I will get. Yes. So if you observe this little carefully, what is this second term you observe first? Just see the second term. There is k a square cos square is there. What is your x? X you see? What is x? A cos. Yes or no? So there is a square cos square. Means this is x square, isn't it or not? So this is same as, if I can write it as k a square minus k. This whole thing you observe.
Yes,
If you
sir.
observe this thing, that is nothing but x square, is it or not? This is nothing but x square. This one I'm telling you. A square cos square is nothing but 6 x square, is it or not? Yes. Yeah. Understood that?
Yes,
By
sir.
half. So half k you take it out. If you take it out, it will be simply A square minus x square. This is your new equation of kinetic energy. Understood this? This is not there in your CBSE textbook. Only this. Till here they stop the equation. Is it understood? Clear? Now we know everything about kinetic energy. Let us now find out potential energy. What is the meaning of potential energy? Potential means what? Potential means an energy possessed by a body by virtue of its position or state. Position.
sir.
There is any position at a height or because of a height or because of a state. Position or state. The energy possessed by a body by virtue of its position or state is called as potential energy. So potential energy is basically because of the position. So position should give potential energy. So potential energy is represented by U. How is potential energy given as half k x square? This is only called potential energy. How did I get this directly? This I will tell you. How did I get this directly? I didn't get this directly. In work power energy, earlier chapter work power energy, you have potential energy formula. Potential is not that MGH formula. Potential energy in general formula is there. In general, potential energy is, of course, you have no idea about integration, but I will just simply say integral force dx. And if you do that, integral minus kx dx. So if you do all this, you will get this. You need not worry about that, how we got this. You just have to remember potential energy for a spring or a S.H.M body is half k x square. How you got this is a
Yes, sir.
little bit of mathematics that you may not understand, but you need not remember this thing. Just have to remember this. So finish. So what is that going to be? Half k. X means we know. X means what is x? A cos omega t plus or minus 5. That's only x. It's not. So you write that a square cos square omega t plus or minus 5. Understood? This is your potential energy. If you see this equation number B and equation number A, what do you see? You see this equation, kinetic energy is having potential energy term into it. So, see this half k x square is also there here. See? Yes or no? Half k x square. You can see that here. Yes or no? Yeah. So that's it. So what do we infer is kinetic energy is equal to half k a square minus, you see this half k is this term, you see half k a square minus potential energy term is there. Did you understand?
Yes, sir.
That's it. So if you see that, so the kinetic energy term is having implicitly the potential energy because it is having that half k x square term in it. Did you understand? Yeah. Now we can
Yes, sir.
let's go down. So if you see this minus potential energy, you'll send it this side. Kinetic energy plus potential energy is equal to half k a square. But we know k, m omega square. Yes. This is called as total energy. Understood? This is very important.
Yes, sir.
Now, if you plot a graph, then you will get to understand what is the graph looking like. What does it look like? Okay. So, this graph, you have some idea in the chapter work power energy also. This was there. So, what is this graph? Potential energy, kinetic energy, I'm essentially plotting it. That's all. Okay. So what I'm doing right now is plotting potential energy and kinetic energy. At 0, 0 means mean position. At the mean position, this is called as mean position. Mean position. And at the extreme position means at what is extreme position? When it becomes amplitude, is it or not? At amplitude, so that is 0 comma amplitude. Yes. So at I would put that point on the x-axis. This is 0 comma a, 0 comma 0 and 0 comma a. This is how it is. Okay? So a comma 0, amplitude comma 0, and here minus amplitude comma 0. Okay, and plotting to point at 0 comma 0 at the mean position. What energy is maximum? Let us see. Write the equations. You will understand which energy is maximum and which energy is 0. Kinetic energy is half. What is kinetic energy? Go back and check. So kinetic energy half ka square minus kx square. Write it.
Square.
Half k into a square minus x square. And what is potential energy? Simply half kx square. So at x is equal to 0, you put 0 here. What happens here? Half ka square minus 0 will come. Because x is 0 now. Understood? Understood that?
Yes, sir.
Do you understand that? Minus 0. So what are you getting? Half ka square. Understood? Now what is potential energy at 0 comma 0? Half k 0 square 0. So at the mean position, velocity is maximum. That's why potential energy is kinetic energy is maximum. Potential energy is 0. Understood? So this line actually represents total energy is equal to kinetic energy plus potential energy. Understood? Kinetic energy plus
Yes,
potential
sir.
energy is total energy. So this is what? So when kinetic energy is maximum, potential energy is 0. When potential energy is maximum, kinetic energy is 0. Understood? So that is what they plotted in your textbook. So that's how the graph came out to be. See, this is maximum. Then one energy is 0. So that's what they plotted like a sine graph. Okay. This is the curve of kinetic energy. And there is another simultaneously one more curve. So what is this curve? This curve represents what is maximum kinetic energy curve. And what is this curve? Potential energy curve. Potential energy is 0, no? Understood? Now it's looking good. Okay, better. Understood that? So when potential energy is 0, kinetic energy is maximum. Similarly again what happens? When kinetic energy is minimum, potential energy is maximum. When does that happen? Let us take. At 0, 0, we understood at mean position. Next, any other position at extremum. At one of the extremum. One of the extreme position. Extreme position means x is equal to amplitude. Maximum extreme position. At x equal to amplitude, what happens? Let us check again. Kinetic energy and potential energy. What is kinetic energy? Half k into what is there? A square minus x square is there. A square minus a square because x is equal to a. Similarly, potential energy half k. X square means what? A square here. Understood? So this is going to be 0. Potential energy is going to be maximum now. Understood? When is this happen? When does that happen? When is x equal to amplitude? At what point does that happen? At x equal to a means at the time period. What? At t is equal to what? At what time is it going to happen? at t by 4, no? At small t equal to t by 4, this happens. Yes. Yeah. So this is the point. Understood? Yes. So you can see, now see, potential energy has become maximum. Kinetic energy has become 0. Kinetic energy has become 0. Potential energy, this is K is 0. Understood? And this is P maximum. Understood? Is it clear what I'm saying? Okay, so this graph, okay, if you want, I'll color it so that you will get this red line. Red line is the potential energy, right? Okay. And this blue line I'll draw this. Blue line. It's kinetic energy. Okay. Now you can see there's a difference. Okay, now I think it's a little bit better. Freehand diagrams are not coming back good nowadays. Digital pen is not so. Otherwise, my diagrams are actually very beautiful. On board. Okay, that's okay, no? Sorry, what happened? Hello, hello, hello. Hello, 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 hello. Hello, 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 hello. Is the meeting started again? Hello, hello.
Yes, sir.
Yeah, what happened? It is showing some error.
I don't know, sir. It must. I think there might have been some network issue or something.
No, when it happens, you re-click it again. Maybe if your internet was this in between, it if it had fluctuated also, it will just cut off. Mine is a very fast internet here. I have a broadband connection. Okay. Yeah, what I was telling till from where you have not listened. Again, see, I colored it for you. Blue and red, I've colored it. So now I
Yes,
think
sir.
it is better. This blue line represents. Just a second. It went down, I see. So this blue line you can see, I colored it for you. My diagrams are not looking so good, but what can we do?
Yes, sir.
So see, this blue line represents kinetic energy, and this red curve represents potential energy. Okay, now is that clear? Okay.
Yes, sir.
So for your understanding, I have drawn it again. I have done it. See, potential energy at one of the extreme position. When is that happening? When x equal to a, that is time period small t is equal to t by 4. Is it or not? That is when the extreme position. At extreme position, what happens? X equal to a. Is it or not? At x equal to a, let us find out the kinetic energy and potential energy. I found out. See, A square minus x square became A square minus A square is 0. And potential energy becomes half k into x square becomes half k into A square. So you see that kinetic energy became 0. You see this? See this curve? This is T by 4. Understood? This is
Yes,
time
sir.
T is equal to T by 4. At T by 4, kinetic energy is 0. Potential energy is maximum. Understood? Similarly, at this point, can you tell me what is this point? T by 2. At T by 2, what happens again? T by 2, you are again coming back to mean position. No, that is
Yes,
why.
sir.
That's why you came back to mean position. That is why what happened? Potential energy again became 0. Kinetic energy became maximum at that point. You can see that. Understood? Kinetic energy becomes maximum. Understood that?
Yes, sir.
That is on one extreme end I showed. On the other extreme end, here, actually 0, T by 4, T by 2. After that, it will go this side. No? After that, it will go back this side. Minus A. Yes or no? This is 0. This is T by 4. Then T by 2. Then T, after that, 3T by 4 will be on this side. Is it or not? Yeah. Understood that?
Yes, sir.
So that is what that graph represents. This graph can be also re-represented in this way also. With only simple graph. We can also draw this graph with a simple graph also. Simple graph by only showing kinetic energy and potential energy in one way only. We're not putting all the time periods, we're just drawing only once. Like a parabola. You can draw like this. Because you see, this is energy graph, energy axis. And this is the amplitude axis. You see here? This is plus A, this is minus A. Understood? And this is 0, 0. Understood that? Yeah. Okay. At 0 means mean position. This is its mean position, is it or not? Mean position. At mean position, what happens? This red line, what I told you about red line? Potential energy line. U of x. Blue line,
Yes,
kinetic
sir.
energy line. K of x.
Kinetic energy.
So at mean position, when x equal to 0, mean position means what? X equal to 0, no? Mean position means x equal to 0. That's only called mean position. Then what happens? X equal to 0 means potential energy is 0. Kinetic energy is maximum.
Yes, sir.
This graph, if you understand, you understood everything. Is it simple? Yeah. So the total energy is simply, this line represents total energy. Total energy. Which is equal to potential energy, P, potential energy plus kinetic energy. Okay. Generally, P and K we don't write. Okay, we generally don't represent by P and K. What is the just for your understanding and writing? But in our actual physics, we don't write P and K. We write K and U. K of
Yes, sir.
x plus U of x. That is the correct way of representation. P and K is just for your understanding and writing, but we should not write like that. Is it understood? So kinetic energy and potential energy are such that one of them is maximum, other will be minimum. Such that they will share that number. They will share their number. For example, the total energy is equal to 10 joules. Then what happens if the potential energy were, if at all, if it were 2 joules, then kinetic energy immediately becomes 8 joules, no doubt about it. Such that the addition will always be same. Because law of conservation of energy. Because of law of conservation of energy. That applies everywhere. Everywhere law of conservation of energy applies. You cannot just simply say any physics equation should and must, any physics system should and must obey law of conservation of energy. Energy is always conserved. Neither energy can be created nor energy can be destroyed. Energy cannot be destroyed. Energy cannot be created. Energy is always constant in the universe. Okay. So these example problems also you try today. Anyway, tomorrow I will tell all the problems, all numericals. I have so many numericals I will tell tomorrow. So today I want to finish off theory, then we will do all the numericals. Okay. So this one you understood. Now next is certain types of oscillators we have. All several types of oscillators we have. One of the oscillator which I already taught to you is only there again. This is spring oscillator, oscillations of a spring, which you know. And you know, simple harmonic oscillators, most important form is simple pendulum. Now we came to simple pendulum. Now we have arrived at that point of simple pendulum. Till now we have done only a normal oscillator and we have done a spring pendulum. Spring mass we did. But till now we have not done about simple pendulum. Now we are going to do simple pendulum. So simple pendulum is simply a bob. Bob means an iron ball, which is simply suspended by a thread. Not thread, string we should say, string. And then what? You give it a push, that's it. You give it a push, it will go to one extreme and then it will start oscillating. It will get an angular displacement theta. So then what happens? It will oscillate. Is it or not? It will not stay there like that. It will oscillate like this. Of course, that bob also will oscillate, but I'm not able to oscillate it along with the bob because you understand. Only that much tools are available here. Right? Yeah. So now having understood that oscillation, now what happens? This is a rigid support. This is a rigid support, and this is a string. In a string, what all are there? In a string, there is a tension force. Tension is a force. It will be that side, in that direction. And along with this tension on this bob, what all forces are acting? One weight mg is acting, isn't it? Obviously, there will be weight acting on it. Weight mg downwards. Along with the weight mg, there will be a, see the pushing force which you gave. Pushing force, you have given a pushing force. Because of that, it went that side. Now, this is called as Lami's theorem. Now, this weight will split up as two components. That day, I think vectors. Vectors. You have idea about vectors? We have to split a vector weight mg into two components. Do you know how to split a vector into two components? This theta, here is this theta, right? How do you split a vector into two components? These are perpendicular components. Perpendicular two components. This weight mg will split as two components. Mg sine theta and mg cos theta. Do you know that? How to split a vector into two components? So this is called as mg cos theta. And this is called as mg sine theta. Why like that? Why two different are coming? Do you know what I'm saying? Have any idea? There is a force like this. It has to be split up as two components perpendicular to each other. They are called as perpendicular components of each other. This is one force. Makes an angle theta. This is mg downwards. So touching component is mg cos theta. How we got this and all that is mathematics. Trigonometry, basic trigonometry. Right now, you need not know that. Means I'll teach you that basic trigonometry again in general class. See how to remember, I will tell you, listen, children. See, there is a theta, no? The theta touching, this theta is touching this component. So that's why it is cos theta component. There is no touching here. There's no touching. So there's a vertical component called as mg sine theta. The touching component is called cos theta, not touching is called sine theta. That's all to remember. Understood? Clear? Okay. So now having understood that, now we can write it. This mg sine theta is this direction. Now, whenever this body has been given a push, it will come back and restore itself backwards. It will come back to the mean position. It won't stay there. It will try to restore itself. Simple pendulum. It will try to restore itself to the mean position. What is the mean position? We can see that. This is called as mean position. Means rest.
Yes, sir.
Even spring also does the same thing, right? Spring also will try to restore and come back to the mean position. Won't stay there only, no. And this length of the string, not spring, okay, string. Let us take the length as L. Let us consider the length of the string is L. And what is the important characteristic and required parameter of the string? I told you, inextensible and massless, massless string we have taken, and it is inextensible. Inextensible, it can't extend, it won't elongate by itself. Okay, so now it is undergoing S.H.M. It's undergoing oscillation, is it or not? So on the bob, on the simple pendulum bob, I'll color that bob. This is the bob. On the bob, what all forces are acting? What all forces are acting? One force is restoring force. Another force is radial force. Is it or not? The bob oscillating about the mean position is undergoing or is being exerted upon by two forces. What are the two forces it is being acted upon? Tell me. One is the restoring force. Restoring force means the force that tries to pull it back to the mean position, this side. Other forces, centrifugal, are also called as radial force, outward force. Yes or no? This outward force is mg cos theta is exactly balanced by the tension in the string. Exactly balanced by the tension in the string. So the bob cannot cut and go away somewhere. Tension T in the string. That's enough. Now what about this mg sin theta? That is the restoring force. That is the restoring force. This is the S.H.M force. This is only the force of S.H.M. Understood that? This is the force of S.H.M. What is actually S.H.M force? F is equal to mg sin theta is nothing but it is equal to ma. But according to our S.H.M equation, which we did earlier, what is S.H.M equation? Minus m omega square x. Remember? Yes or no? Minus m omega square x. Remember, this was the equation of S.H.M, right? Yeah. So we have to get this equation in this form. Then only we can say it's really in S.H.M or not. Understood or not? It is in S.H.M, I am saying. But if it is in S.H.M, it should become this way. It should form this way. Understood? So let us now understand how does it really, is it really representing S.H.M or not? It's oscillating, no doubt about it, it's oscillating. But it is S.H.M or not, we still don't know. Understood that? So this angle theta is very small angle. Small angle. For very small angle, what did I tell you that day in class also? Sin theta becomes almost equal to theta. Only for small angle. When the bob is given a very small angular displacement, then this happens. This is true. Understood that? Is it understood? Now you see the bob. It's the bob. Bob means the spring, metallic ball, on which one force, restoring force is there. What is that? Mg sin theta is trying to restore it. Now on that bob, from the rigid support, there is a length L. Now it is trying to restore itself backwards. What does it mean by restoring itself backward? It is doing an angular displacement, isn't it or not? It is doing an angular displacement means it's acted upon by a torque. A torque is acting on that. Torque, what I told about torque in the earlier class. Torque about the support or torque about this rigid point. This is called rigid support, no? Rigid support. Or fixed point, torque about the rigid support. What is the torque acting on it about the rigid support? Torque is given by what? What did I tell you about torque? R cross F. What happened again? Hello, hello. Hello, 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 hello.
Yes, sir.
What happened suddenly? Your network got.
Yeah, sir. I don't know what's happening. I think there's some issue.
Your internet
Maybe
is
because
only
there's no
on.
signal.
Yeah, till where from you did not listen? Did you listen all this?
Yes, sir. I listened to it.
So torque about the rigid support is given as R cross F. Here R represents the radius vector. R represents here L actually. And here F represents this one. This is F. R cross F means L cross mg sin theta. Understood? Yes. So that is the torque. The torque about the rigid support is entirely provided by the tangential component, is it or not? The tangential component or the restoring component is giving rise to torque. Yes or no? So this cross product, if you see, L bar is in this direction. F bar is in, L is not a bar actually. L is a R bar actually. So L and how they are restoring, it's a restoring force. So restoring force is a negative thing. So that is why we are writing minus mg. Why we are writing is restoring force is in the opposite direction to displacement. That is why it is like that. Understood that? Is it understood? So now if you write the torque tau, what is it called? Minus L. You understand this? L, why did I write cross and then I made it as like this without cross? See, L and R are exactly, L and mg sin theta are exactly perpendicular to each other. So there is no angle between them. Do you understand? And why that negative? Why did I put that negative? Did you understand? Why I put that minus? Because restoring force is opposite to the direction of the angular displacement. Angular displacement is in this direction. Restoring force is in ulta direction. Negative, reverse direction. That is why the negative came. Is that understood? Okay, that is why the negative came. You want me to write? I'll write that. Negative sign is because of restoring force. Is opposite to restoring force opposite to the angular displacement. Angular displacement. Right? Understood that? So that is the reason. So now tau is equal to this is the reason. Tau is equal to minus L mg sin theta. Now we know from first year intermediate, earlier chapter, what is it? Rigid body dynamics, rotatory motion. Torque has another equation. Torque actually has another equation. Is equal to moment of inertia into alpha. Alpha is the angular acceleration. This is nothing but Newton's second law of motion. It's also called as second law of motion. Newton's second law of motion for rotation. It's also called as Newton's second law of motion for rotation. Or we can also call simply tau. Tau is equal to I alpha from rigid body dynamics. We know that. Now if you equate these two, yeah. Yes, yes. What are you saying? Alpha is called what? Angular acceleration. So now I alpha is equal to now what? Minus L G sin theta. I equated both of them. Is it understood till here? So what is alpha? I minus mg.
Minus M.
Do you understand that?
L by
Now we know
I.
that since
Yes, sir.
sin theta is almost equal to theta for very small angles. For very small angles, this is not true always. Very small angle. Then what happens?
Yes, sir.
Alpha is equal to minus mgl by I. Sin theta becomes theta. Understood?
Yes, sir.
Now, if you observe this equation, you just observe this. Observe this equation. What do you see? What do you infer from this? It appears like, it is similar to this, similar to S.H.M equation. Why? In S.H.M equation, we have acceleration A is equal to minus omega square
Yes,
x. Similar to this. So that means if you comparing with this equation, what do you infer? Omega square should have been mgl by I. Yes or no?
yes, sir.
That's it. Okay, yeah. That means we got omega equation. GL by I. Understood? So if we got omega, you got time period and everything else. What is time period? 2 pi by omega. 2 pi by omega means root over I by mgl. Did you understand that? I'll write it neatly. 2I by mgl. Understood? This is time period of oscillation of simple pendulum. But as the simple pendulum, now since the string of the simple pendulum is massless, I told you that the string of the
Yes, sir.
pendulum is not having any mass. And the moment of inertia is simply, what is moment of inertia? Actually, different formulas are there for some moment of inertia. Mr square by 2,
Yes, sir.
Mr square by 3, 2 by 3 Mr square, 2 by 5 Mr square. So many are there. But let us consider the bob is very small. The bob is very small. Then the
Yes, sir.
moment of inertia will be what? Only ml square. There is no mr square,
Yes,
it
sir.
will be simply ml square. Okay.
Yes, sir.
Then if you substitute that, what do you get? Root over square by
ML square by MGL.
cancel,
Yes, sir.
by root over L by G. Understood? But this is not always true. Okay. This is not always true. If the bob is very small only, this is true. Otherwise, it's not true. Otherwise, something else. That also, if it's when it's not true, that also I will tell. If the bob is big, the bob is big enough, then it won't be simply it will not be that. No. What will it be? You know what is the moment of inertia of a sphere? 2 by 5 m r square. This is the moment of inertia of a sphere. Remember that. And what is this r? Small r is equal to radius plus L. This is the value. So this is the moment of inertia of a sphere. Sphere. Here it is a sphere, right? So if it is big enough, the moment of inertia is not equal to simply ml square. Okay, ml square won't work because these type of problems are there in 8. That's why I'm telling you. Understood that? Is that clear?
Yes, sir.
Sometimes it will be 2 by 5 or 2 by 3 sometimes. When is it 2 by 3? When is it 2 by 5? Do you know? This is for solid sphere. Solid sphere. And this is for hollow. Hollow sphere. Okay. Two types of spheres are there, no? Hollow sphere and solid sphere. You know that hollow sphere means nothing is there inside. Solid sphere
Yes,
means
sir.
fully solid. This is solid. Solid sphere. Hollow means nothing is there. Pani puri. Empty sphere.
Yes, sir.
Tennis ball. This is tennis ball. This is cricket ball. Okay. So both are having different answers. For hollow, it is 2 by 3. Solid 2 by 5. Okay. Did you understand
What
this?
happens if it's semi-hollow, sir?
Semi-hollow, which is also called as semi-solid. That is totally different. That is called as, those all problems will come in IIT and all that. You won't have it anyways. But still, semi-hollow means in which way it is semi-hollow. That also we should know. It will have something like this, like your annular. It's called annular sphere. This is called annular sphere. So little bit of solid and little bit hollow inside that. That is called annular sphere. For that, there is a formula. There is a formula for that. The moment of inertia is given as m into. See, these are two radius, no? R1, R2. So m into 2 by 5 or 2 by 3? 2 by 3, m into R1 square plus no, R minus, R1 is bigger, R2 is big, R2. So m into R2 square minus R1 square, 2 by 3. This is the formula. This is there in your textbook. These formulas, all these formulas are there in your IP textbook. If you turn back, no, all 94 formulas are there. In that in moment of inertia, also several 28 formulas are there in your textbook. In out of the 28, one of them is this one. Okay, did you understand that? But that is not important for us. This is not comfort need. Okay.
Yes, sir.
Now we have done
Yes,
till
sir.
now almost major part. Now what is there in this chapter is only 2 more parts. Out of that, one is not important for NEET. But it's not there for NEET actually. 8.1 damped simple harmonic oscillator is there for your NEET. After that, what is there? No, 8.10 forced harmonic oscillator, that is not there. It's removed from your NEET syllabus. Even for IP syllabus also it's removed. It's not there. It's not coming in exam. Okay. But anyway, just for your understanding, I'm teaching that so that tomorrow we can start the next chapter. So I'm just teaching so that little bit you try to understand. Purely mathematical. What I'm teaching right now is purely mathematical. But that's why it's not there for our NEET. It's removed from our NEET. And it's also removed from IP book also. IP syllabus of this year exam is not there. Okay, but still I will just tell you for understanding purpose. So now let us see what happens here is damped harmonic oscillator. Damped means a lot of air is there in your room. AC room full of the density of the air is more, right? In an AC room, density of air is more. You can do this experiment at home. I think many of you people have some type of what do I call that? In Archie's gallery, we get some type of oscillating thing like this. A toy-like thing which will move up and down, it will move. It's like a spring. A spring will be there like this. And here some toy will be there here attached. Many of the people have seen in their house just like that they keep it. So you can do an experiment with that and you can understand what I'm saying. So now you've taken a spring actually. Essentially, this is a spring with a body of mass M. Okay. And there's a pointer, and here on a scale, you're marking what I'm telling you is damped simple harmonic oscillator. Damped simple harmonic motion or simple harmonic oscillator. What is this damped simple harmonic oscillator? Let's try to understand. This is spring. Spring balance. Basically, spring balance. We can buy all.
Yes, sir.
So you see the spring balance.
Connected to hotspot, sir. So it's depending on my mobile signal.
Yes, I know.
Yes, sir.
At least some time is there. So spring balance, you are essentially taking a spring balance and you're connecting a pointer and you're connecting it to scale. This is scale. And you pull the spring balance a little bit. when you pull it, what happens? The spring balance will oscillate up, down, up, down. It will oscillate like this. It'll go up, go down, go up, go down. This is everyday observation. I told you you can buy such a thing in Archie's gallery. Archie's gallery, this all this type of gift articles and all that will be there. There you can buy this. So what happens is it will go oscillate up, down, up, down, up, down, and oscillate. You do this experiment in a room where there is no air at all. Like you do it in a now is the best time to do this experiment because it is summer.
In a vacuum chamber.
No need a vacuum, even in a room where it's very hot room. Kitchen. You do this in kitchen and you do this experiment in AC room, air conditioned room. In air conditioned room, the air is large. The density of air is very large. So now what happens is, now see what happens in air conditioned room when you do the same experiment. A lot of air. You see this dot is air particles, air molecules. So when you do this, they will touch the air molecules, right? The air molecules will stop it. No, it will not stop it. Air molecules reduce their speed. Is it or not? When air molecules touch them, touch the oscillating body, slowly it will slow down, slow down, slow down, slow down. Yes or no? That is what is happening. These air molecules are touching and slowing down, touching, slowing down, touching, slowing down, slowly to slow down. But the same experiment you do in kitchen, no, there is no air much. There is not much of air because kitchen is generally hot. In a hot situation, there will be not much of air there because air will not be there. Air always escapes. I hope you know that much, right? In summer, why can't we breathe very well? Because less air is there at the.
Yes, sir.
In summer, why do people try to go to Goa, hill stations and all that? Because air will be more at the. Because more oxygen is there on the top of the hills.
It will be at higher altitude.
So air will try to escape to higher altitude. In winter, can you be on the higher? Can you be on the top of hill? No, you must be on the bottom of the hill. Why? Air will try to come down in the winter. Air will come down because the top on the hill, on the top of a hill, air is less actually in winter. This is winter. And this is summer. So in summer, you have to go on the top of a hill. In winter, you have to come down the hill. Because down the hill, more air is there. Up the hill, less air is there in winter. So that's the reverse thing. So the same thing here also. In kitchen, less air will be there. In air conditioned room, more air will be there. So denser the air, the oscillation will slow down very fast. Very fast, it will come down to zero. It will come down to rest. So why is it happening is there is a damping force acting on it. Damping means, you understood? Damping means reducing force. A force that is reducing your oscillation. What is that force that is reducing your oscillation? Air damping. Damping due to air molecules. Air molecules. And the damping due to air molecules is only given as a force. And it is proportional to the velocity of, and it is given by an equation minus B into V. V is the velocity. Okay. This is called as damping. Forced damping. Okay. Forced due to damping is given by minus BV. Now, total equation of oscillation is given as Newton's second law. F is equal to MA. Is equal to what? Minus BV. And minus, we know already one thing is already there. Minus m omega square x. Is it or not? J is minus kx. Is it or not? Minus kx. So we got it. Understood this? Minus kx is because of already there. Ma is only called as minus kx. No. Plus extra term we added. Understood? Minus bv we added here. Is it understood? Little bit. This is only confusing. This is mathematics. No? What is the acceleration called as? dv by dt is equal to minus bv and minus kx. Is this understood? Is equal to minus v minus kx. V means what? I told you this is nothing but d square x by dt square is equal to minus bv. Is this understood? You just don't have to remember what is all this. You just have to understand a little bit. This is not come in exam. Don't worry. This is not going to come in exam. It's removed from syllabus. Just for your understanding. I'm telling you. Yeah. You're telling something. This is not there in exam. Just for your understanding. I'm telling this. Okay. This is given as this equation can be written as. This is a big mathematical equation, children. It's very strange to write it, but you have to understand it. Just have to understand that. So no need to remember this. What is all this and all that? Just have to understand. Little bit you understood, no? That's enough for you. Damping will reduce the oscillation. How it will reduce? Final answer of omega. Earlier what we got root k by m, no? Minus something must be there. Omega will reduce, no? Minus b square by 4m square will come. This new term will come. It is called damping term. It's called as damping term. Damping is that which will reduce, okay? Not your English damping. Damping in English means wetting the surface, not that damp surface.
Yes, sir.
No? Not that. In physics, damping means reducing term or a resistance term. Okay, this is the damping. The damping term. This you need not understand, but all you have to understand is that what happens in air. When there is air, it will try to reduce. So this oscillation will be like this. It will be reducing like this. Finally, it will reduce. Understood that? This is what we have. Next, forced harmonic oscillator is there. That's not there for syllabus. So you need not bother about it. Only last resonance I will tell you. You need not worry about forced harmonic oscillator. It's not there in syllabus. Resonance is there in our syllabus. Resonance is a very simple thing. This also in Archie's gallery, you have seen this resonance concept. You take several pendulums of different lengths. Pendulums of different lengths. And when you oscillate it, no? When you oscillate, what will happen? Two of them which are of same length. You see, this and this of same length. When you oscillate, it will move like this, right? Those which have same length, they will oscillate very much with very high amplitude. It's oscillate like this. Those two which have, are you understanding what I'm saying? The one which has, I'll draw that as a straight line. So this will oscillate like this. Do you understand now? Now you see. These two have same length, no? They will oscillate high frequency. Do you know this example? Very useful example I will tell you about resonance. This concept is called as resonance. Resonance concept. Another way to understand is, do you know the soldiers when they march? It's written in your book also. It's written somewhere. Soldiers when they march on a
Sir,
bridge.
like I currently don't. Sir, I currently don't have my book on me.
No problem. Forget about it. I'm just telling you. Soldiers when they march on a bridge, they are given instruction. They should not march. They should not march on a bridge in a synchronous way. They should march. They'll say march in a normal way or march without synchronous. Why? If they march synchronous, what happens? The bridge will break. Bridge will break. It's possible that the bridge will break. Why? Because the vibration of the foot vibration and the bridge vibration, if it becomes equal, what happens? The bridge will oscillate like this. Bridge will oscillate up, down like this. So bridge may break. That is why they say all of you go out of synchronous and just walk freely. Don't march on a bridge. Don't ever march on a bridge. This is everyday observation. Yeah. So that's my best example. That resonance concept, you should understand that when the natural frequency is exactly. Oh God, I lost my connection. power gone. Hello, hello, hello.